Hi, I'm Rachael Livermore in Melbourne, Australia, and I am joined by my fellow host, Dr. Jeff Silverman, who is in San Francisco, California.
Hi, guys. And we are joined today by Dr. Ashley Pagnotta, a professor at the College of Charleston.
Hi, I'm Ashley. I am in Charleston, South Carolina.
So, what we wanted to talk to Ashley about today is some really cool stuff she's been doing with supernovae. So, let's start with what are supernovae and novae, and what is it you're looking at?
Sure. So I study a couple different type of exploding stars. All of them have one similar star. So all of them have a white dwarf, which is like the ember of a dead star. So it's what's left over after a star has used up all of its hydrogen and burnt off all of its normal fuel. So you're left over with this ember, this white dwarf. And then all of these white dwarfs have a companion star with them. And they're really close to each other. And the white dwarfs have really strong gravity. So they pull hydrogen gas from their companion star onto the surface of the white dwarf. So once that happens, you can have a couple of different events. If there's just a small little eruption on the surface, we call that a nova. And if you have a big eruption where the entire white dwarf blows apart, we call that a type 1a supernova.
So, how do you go about finding these things?
So the stars that I tend to work with, we let other people find. There are a bunch of different teams of astronomers who run these incredible surveys where they watch the sky every night and they look for changes. So I let them find them, and then what I'm interested in is what these objects have done in the past. What did they look like hundreds to thousands of years ago, and how does that tell us about their behavior in the future?
So, do you have a TARDIS, or how do you figure out what things looked like 100 years in the past?
I wish I had a TARDIS. That would be amazing. No, so we use a really unique data set that is the old archival plates. So now when we look at the sky with telescopes, we take pictures with basically really nice digital cameras. But before there were digital cameras, we used these glass plates. It's like taking photographs on film, but just with glass instead of a flexible film. So the Harvard College Observatory has about 500,000 of these plates that they started taking in the late 1800s and continued through till the 1980s. And so when we want to see what something was doing in the past, we can look on those plates and follow the evolution of that star through its lifetime.
So those plates are, up to 100 or 100 and something years old. But how do you look at stuff, what these stars were doing thousands of years ago? You mentioned that.
So, for example, there's a star that we have records of in old Korean texts, and we have records of that nova. And we wanted to find exactly what star it was that erupted. We knew based on the ancient records, the general location in the sky. We knew what constellation it was in and kind of what stars it was near. We wanted to know exactly which star it was. And so what we can do is look for what we call a proper motion. So we were looking for a star that used to be where the ancient text said that it was, but over the course of the last few thousand years has moved through the sky. It's in a different place now. So we could compare an observation from now with an observation from the early 1900s and say, okay, well, it moved this much in the past 100 years, and then work that back to where it would have been before to match up with the position from the ancient astronomers.
That's pretty cool that you're using ancient astronomy texts to do like real modern science.
Yeah, it's a really impressive record. The records of the Chinese and the Korean astronomers are very extensive and very well documented.
So getting back to these Harvard glass plates that you talked about, they have a pretty interesting historical significance as well as scientific, right?
Yeah, they do. One of the neat things about the early days of the Harvard Observatory is that the scientific staff that they employed starting in the late 1800s, was almost exclusively women. So Edward Pickering was the first director to start hiring women to work in the plate stacks. He found that they were very meticulous and very good at cataloging the stars and keeping track of the brightnesses and doing the work that needed to be done. And so they were what at the time were called computers, and we still use their results today. So there are results that we use for big science and measuring distances across the universe, understanding the life cycles of how stars work. That all comes from the work that they did classifying these early stars, sky surveys, and figuring out, how the stars changed over time.
So imagine you're an astronomer like 100 or 1,000 years in the future. Like, what kind of records are we producing today that are going to help people in the future track like the history of explosions that they see?
Yeah, so big surveys are very trendy in astronomy right now. There are a couple of different collaborations who have surveys running in both the northern and the southern hemisphere. So the big one that's expected to produce sort of really mind-boggling amounts of data is the LSST. And they have been working with tech companies, with Google and with other tech companies who are really masters of data science and data storage, to store all this data, to make all this data accessible, and to use computer intelligence, AI, machine learning, those kind of things to access this data.
So it's interesting how astronomy has scaled like over the last century, and we've gone from human computers measuring individual stars to having to train like machine learning algorithms to work with huge amounts of data of the entire sky.
Yeah, in just 100 years, we have switched from like looking at a photograph with a magnifying glass to teaching our computers to process gigabytes of data so that they can tell us what's in there.
Yeah, very near and dear to my heart as a data scientist nowadays, so very cool.
Well, thanks so much for chatting with us, Ashley. This has been really interesting.
Yeah, this has been great. Thank you for having me.
Cheers.
Yeah.
All right, well, we'll see you all next time with another astronomer guest from somewhere around the world here on Three Body Problems.